you a bit of some of the summer research that I've done. Now, you bear with me because I actually have a little bit of a stutter, but I'm going to do my best. So anyway, the research that I've been doing the past 2 summers, it's been on mainly teleparallel gravity theory, and I've done my supervisor for this research has been Dr. Robert Vandenhoegen, and we've also done it with 2 other students as well. So I'll start then. So first, before I talk about the actual research that we've done, it's important to understand why we're doing it in the first place, and then to gain a little bit of an understanding of what is actually teleparallel gravity theory. So the main motivation behind our research, like it actually goes back to how the universe is expanding, and that it's actually expanding at a quickening rate. So we'll go back to the beginning before we even talk about teleparallel gravity theory with just the theory of general relativity, which Einstein published back in 1915. And basically, this theory, he mainly explains through it that he explains gravity as being a geometric property of space and time. So when we think about space, that's the 3 different dimensions, like in 3D, and then time ends up being the 4th dimension. So we end up with a 4-dimensional system. And he explains the dynamical features of gravity through the curvature of 3-dimensional geometry. And basically, he's explaining that the curvature of space-time, that it's related to the energy and momentum of the matter and radiation that are present. And he explains that we can represent this relationship through the Einstein field equations, which end up being partial differential equations. So really, we're able to use general relativity to explain a lot of different things that go on in our own solar system. We can look at a lot of the physical properties of gravity, such as how, like, when they're coming towards the Earth, how the Earth's gravity will actually change the motion of that asteroid. And probably the best, or maybe an analogy to explain general relativity. Say if you have like a ball that's sitting on a table, and then you cover it with a blanket. That blanket's wrapping around the ball. So that's almost like how space-time is being wrapped around the mass like of an object. So that object's mass, that's actually like affecting the curvature of space-time. And then when you look at that system of differential equations, the Einstein field equations, when we look at certain specific examples, some of the exact solutions to that system of equations, we can look at those solutions to explain rotating black holes, and then we can try to use them to explain the expanding universe. Now, as I already mentioned, general relativity is very effective at explaining the physical properties in our own solar system, but it starts to break down when we look at the accelerated expansion of the universe. And where it breaks down is the fact that it has to introduce dark energy to explain it. Because when you think of gravity is an attractive force. So why would the universe be expanding at an accelerating rate? Like, you would think that as things are being pulled together by gravity, that rate would actually start to deaccelerate. So basically, scientists are starting to notice that, like, as we continue to do research about what's going on in the universe, that general relativity might not be the best way to explain everything. And so we're trying to improve on general relativity. We're trying to find a theory that can better explain what's going on, like in the whole universe. Because if I go back to the Einstein field equations, when Einstein was deriving these equations, he had to use a cosmological constant right out front here. But really, there's no way, like, that's not a physical property that we can observe. Like, it's kind of just a mathematical constant that we had to put there to make the equation work. So right now we're trying to develop better theories of gravity where we don't have to put that constant in, like, right in front. We're trying to find a theory that can explain gravity completely in one mathematical concept, and where we can measure all the physical properties of it and then put it into one concept. So I just wanted. So here's kind of an example of where relativity does a good job of like explaining a concept in our own solar system. So it shows how space-time will be affected by the mass of the sun, and how light also follows the contours of space-time. But then when we get into the expansion of the universe, so with the Big Bang, the universe started as an extremely hot and dense point of concentrated energy, approximately 13.8 billion years ago. And then we know that there was the inflation period where the universe expanded outward very rapidly. And that expansion has continued up till the present time. But what we're trying to figure out is, why is it expanding at an accelerating rate? And so, now, if we make the assumption that general relativity does explain things correctly, the only way to make general relativity work for it to be able to explain the acceleration, like in the expansion of the universe, general relativity has to introduce dark energy. Now, dark energy, when we think about it, I guess scientists believe that it permeates throughout all of space, and that dark energy is like an invisible substance with no light, and they believe that it makes up 95% of the actual, like, of the total amount of matter in the universe. But like, if we can't see it, then how do we really know that it's actually there? Now, we're not saying that general relativity is wrong, but we're just saying that maybe there's a better theory that would be able to explain everything. Because it's quite possible that when we look at different things going on in the universe, and we say, oh, that must be caused by dark energy, that could actually be an illusion that gravity works differently than how Einstein believed. So basically, that's kind of the motivation behind our research, to maybe to find like either a better theory for explaining gravity, or to build off of general relativity. And so that kind of takes us into teleparallel gravity theory, which is, in a sense, just a new approach to explain gravity. So towards the end of his life, Yes, so Albert Einstein hoped to unify all the laws of physics within a single mathematical framework, because on one side he had gravity, which he had already developed through general relativity, but on the other side he had the electromagnetism properties of like with magnets and then electrical currents and light itself. And so if he was committed to developing a theory that would be able to better explain like all the laws of physics, and he actually attempted to develop teleparallel gravity theory, but he ran out of time. And then you might ask, like, what's the difference between teleparallel gravity theory and general relativity, and why is it even different? So, like, why is it something new that we should look at? And basically, parallel gravity theory looks at how torsion affects gravity. It's like the rotation of an object, not just the energy and mass and momentum that it has, but how also its rotation like affects space-time all around it. So we look at the torsional field of an object. So it's the force field acting on objects that are in translational and rotational motion. And we think by incorporating torsion that it will be able to better explain if some of the things that are lacking with general relativity. Right now, people have been doing research on teleparallel gravity theory for a bit of time, and they're starting to notice that it can better explain some physical phenomena, such as the accelerating expansion of the universe, and then also um, the singularity within black holes. And so in general, they believe that teleparallel gravity theory will be able to that through it we'll be able to develop a better theory to explain gravity. Now, getting more towards what we're doing specifically in our own research, teleparallel gravity theory would really be a big topic, and we can't cover all of it. So we're going to be looking at we've been looking at a generalization of teleparallel gravity theory called F of T gravity, and that's just where this torsion constant, which we find in the rotation of objects and in the twisting of space-time itself, that the F of T is actually just an arbitrary function of that torsion scalar. Now, just to explain again the difference between teleparallel gravity theory and general relativity. So general relativity is mainly just space-time curvature. So it's the distribution of matter. So think of the sun sitting on a blank sheet, and then how that sheet will start to curve around it. But with teleparallel gravity theory, we have really that center object, it's starting to twist the sheet. So think of it almost as if you're wringing out a wet cloth or something like that. And it's almost like a tornado structure in a sense. Now, Einstein never believed that teleparallel gravity theory would be able to explain like all of the physical phenomena present in the universe, but he did believe that it would be a better theory to explain gravity, and that's why he started working on it. But unfortunately, he passed away. So right now, we're also developing something else called string theory, where we believe that particles are like vibrational strings that form loops in space-time. And we believe that theory may be able to better explain much of the different physical phenomena within our universe, so that it could actually explain like all the different laws of physics. And right now, people are trying to link teleparallel gravity theory to string theory, because together we will be able to unify like all the laws of physics within a single mathematical framework. So again, going back to it, that we're definitely not saying that general relativity is wrong. And at the end of the day, it's perfectly possible that dark matter may exist out there, and that's the reason why the universe, like that that it's expanding at an accelerating rate. But because it's not possible to view it, that makes it extremely difficult to study. So we're just trying to develop a better way to, to explain gravity that might encompass general relativity, plus be able to explain the expansion of the universe, black holes, and then other things, like in a mathematical and geometrical way. So now, as I already mentioned, teleparallel gravity theory is definitely a big topic, and like there would be a lot to cover with it. So we were studying a very specific dynamical system called the Bianchi Type 5 model. That's part of FFT gravity. And the main assumption with that is that a certain parameter value, the parameter, the m value, that it's equal to 1. And we're hoping that in studying that very specific cosmological model, that it will help us to better understand teleparallel gravity theory. So basically, this dynamical system, the system, once we played with the equations and everything, and I'll tell you, last summer when we first started with it, like it took a long time just to even derive the equations, because what we're doing here with this case, it's new, because people had always been studying teleparallel gravity theory, but they had never really incorporated the spin term into it. So by incorporating that spin term, we were hoping to get new properties and results. So last summer, we spent time deriving all the equations and everything, and we eventually got down to a dynamical system of 4 dimensions and 3 parameters. So here you can see the different 4 variables we have, and then the 3 different parameters. Now, the 3 parameters, they have specific ranges of values. So for the k constant, like it has to be positive, going from 0 to positive infinity. For mu, it had to go from negative infinity to positive infinity, and then the same with f prime. So mu and f prime could be anything, but k very specifically had to be a positive number. And then the 4 variables, we used them to solve for the equilibrium points of the dynamical system. So I'll jump ahead to show you the different differential equations we had. Now, I'm not sure how much all of you know about like dynamical systems, but the goal with the equilibrium points is to find values for those 4 variables that would make that would allow all of these differential equations to equal 0. So like, and you have to use those specific values. Like you have to plug them into each of these equations, and then we want to go like all the equations to equal 0. Then once we found those equilibrium points using algebra, we wanted to study the behavior of the system near the equilibrium points for different values of these parameters. Because what I mean is that those parameters, like even at the equilibrium points, that they can still be anything, like within these range of values. And then once we go along that range of values, the behavior of the dynamical system might change. So kind of, like our objectives for this summer, we want to first solve and double check all the equilibrium points. Then we were going to look at the behavior of the system near the equilibrium points, because one of the properties of this dynamical system was that near the equilibrium points, the behavior of the dynamical system would be a representation of general relativity plus teleparallel gravity theory. So we thought by understanding of the system near the equilibrium points, that it would give us a better understanding of how those two different theories kind of come together, and maybe be able to build off of general relativity. And then we want to verify our calculations for the equilibrium points and then the behavior of the system by using numerical computation, like on our computers. And I'll get into that more next week when I show you the results of our research. And basically, like the end goal of our project, we're not looking to create a new theory for gravity. We're more just looking to get a better understanding of teleparallel gravity theory by doing of this analysis. And then we're hoping that in presenting that to others, that eventually that may help people down the road develop a complete theory to understand gravity. You can see just the different differential equations again, and then it's just some of the different variable values, that went into these equations. And I apologize for the writing. I wrote it out by hand, and I don't have the neatest handwriting. But anyway, but you kind of get the gist of it, that there was a lot going on. So next week I'll kind of get into like a bit on how we accomplished the dynamical system analysis, and I'll provide a better description of what is a dynamical system. So basically, this week I talked about more the physics side of it and the motivation behind our research. And then next week I'll get into like the actual research we did and the math behind it. And then here are my references for it. But yeah, that's everything. So if anybody was confused or anything, feel free to ask any questions.
Thank you very much for that, Simon. It's very impressive work you're doing. And I applaud you for it. It's also very exciting. Also, like, I'll admit I definitely got confused. But I think you had a really good explanation of general relativity. I don't understand it very well, but like, I just thought it was like brief, simple, nice, straightforward. And I know you say you want to become a professor one day, and you enjoy teaching, and I think you're going to be fantastic at that. So,
okay. Yeah, well, thank you very much. I appreciate it.
Yes, I was saying the same thing. Like,
oh,
as somebody who hasn't taken like anything past high school physics or math, I was like surprised by how much I was able to understand. It was like really well explained.
Oh, well, yeah, yeah. Thank you, guys. Yeah, that was the goal anyway.
Um, I have to rewatch your presentation for sure so I can fully grasp it. Um, okay, can you help me just try to understand this a little bit better for a sec here? So general relativity is this idea that space and time are linked into some, would you say, geometrical property or figure of existence, like space and time are this thing creating a 4D block universe. Is that
Right. And we
in
think that the curvature of that is caused by the energy and momentum of all the matter and radiation that's present.
Yes.
Yeah.
And then can you just sorry, but briefly just try to explain how teleparallel gravity theory fixes it. So it's going beyond just the distribution of mass and things like that to add, is it what? What is it adding? Or
Um, it's more looking at the twisting of those four dimensions and like the rotation of it. Like the think with general relativity, it's more like laying it out on like a flat like a flat blanket, let's say. And that blanket is just wrapping around like a ball where with teleparallel gravity theory, because of the rotation of that central object, that's twisting that fabric of space and time, and you get like kind of like a tornado. Yeah, that's the best description I can give.
mm. And uh yeah, I don't want to be pretentious here, but in general relativity, like the speed of an object alters, I don't know how it relates to time, correct?
Yeah. Yes.
And so if you're talking about like the speed of some mass like rotating, how does that differ from just talking about speed in any direction? How does the rotation differ from, like it's almost like distance traveled, but you didn't actually go anywhere because you just rotated.
Right. Um, like I think it's more that let's say with general relativity, like think of it as like an asteroid in a sense. Um, Looking at just general relativity, like we can see that it'll get pulled in by the Earth's gravity because the Earth is almost warping that sheet of space and time. Um, but then with with teleparallel gravity theory, like it's almost like it's twisting that space and time, which is creating like another field in its own, and it's called a torsional field. And then we think that torsional field that that's almost creating another force of attraction.
And what can you see this torsional field do? Like, do you see it cosmologically doing anything to objects? Like, can you give some examples of like its causal power?
Um, okay, now that's where we're really kind of running into trouble. Really, like general relativity and teleparallel gravity theory, they're very similar when it comes to much of our like everyday observations. Really, we can only get a good grasp of the difference between them when we study the Big Bang and the very beginning of the universe. And then and then when we look distantly into the future, plus the behavior around black holes. So I would say that really the main difference between them, it comes down to the underlying mathematical formulas that are involved. And then when we look at the behavior like at the inside of like on the inside of black holes, for instance, or with the beginning of the universe like the Big Bang, like a lot of the um laws of physics that are involved in general relativity, they kind of start to break down. Where we think with teleparallel gravity theory that it'll just better be able to, like that it'll make it easier to explain those things, and that it'll actually, like, we hope that those mathematical equations won't fall apart.
So are you, if I understood you correctly, are you saying that the Einstein field equations don't work inside of a black hole? Like they don't describe the behavior of a black hole? Is that what you're saying?
Kind of. And yeah, that we have difficulty in understanding the behavior within a black hole just using the Einstein field equations. But we think, like with teleparallel gravity theory, with that torsional field, and not having that cosmological constant, we think that that it'll actually be able to hold together in a sense.
And then I guess another question I have is, you mentioned that, the acceleration and the change in the acceleration of the universe,
Right.
aren't excellently explained by general relativity. I don't know if you addressed it, but how exactly does teleparallel gravity theory, help maybe explain, the rate of expansion of the universe?
Okay. So with general relativity, we kind of have to make that assumption of that dark energy came along, and the repulsive forces of dark energy, they overcame the attractive forces of strictly gravity, like without dark energy, and that those repulsive forces caused the universe to like expand at an accelerating rate. So like that's what we think for general relativity. Now with teleparallel gravity theory, I'm not really sure on the specifics on how it's better able to explain it. More just that when we plug it into supercomputer models, let's say, like when we use the different structures of it, and when we use it to model things out, we see that it works to explain the expansion of the universe, and we don't have to include dark energy into that explanation.
Okay. Sorry, I was talking to you to say thank you, and I was muted. I'm gonna send my comment that I was typing during your presentation, so please ignore the second part of that comment. Okay, so just a broad question I have for you to get philosophical, I guess, but it's an important question to think about, of course. I wrote a difficult and important question. Do you have any idea how your work will be applied to society in the near and or far future?
Yes. Okay. When I was doing research for this presentation, so I actually read up on how right now the belief amongst the scientists is that like eventually, with the universe continuing to expand at an accelerating rate, we'll get to the point where things are so far apart that stars will no longer be able to form because dust and gas will be so diffuse that like eventually the universe will turn into a cold and dark place. Now, granted, that's still 5 billion years in the future, and I'm sure we might, if that the human race could very well be wiped out before we get to that point. But in developing teleparallel gravity theory, we're hoping to get a better understanding of how that'll come about, and when it'll come about. So and not that we'll be able to to prevent it or anything, but maybe just in giving human beings, if human beings, the comfort that we know what's going to happen. Like, I think that'll be how we'll best contribute to to um to society.
I like that answer, and that's definitely a far future kind of answer, I think.
Yeah.
So something else I commented, I don't know if you can like see my comments right now, but I wrote that postulating dark energy and dark matter feels a little bit like using a deity to explain away observations. Like sometimes I think of someone talking about a miracle cure for something, or like, a patient overcame something miraculously, and we say, oh, that must have been the work of some deity, whatever you believe in, right? Whatever your religious divinity is.
Right.
Do you see any similarity to saying, oh, well, we don't know what exactly this repulsive force is, or oh, there's this source of gravity and we just don't know where it's coming from. There must be some kind of matter or something which is just unobservable. Like, are they suggestive? Does it feel like that at all? Like that you're almost like suggesting some unobservable thing is there, but it's like maybe your teleparallel gravity theory suggests that, well, it's not an additional thing there, it's like an additional force, or just a way that gravity behaves as a result of rotation or something like that.
Yeah, that's kind of the feel that I got for it too, that like we were like we were so happy with general relativity because it explained so many different physical things going on in our universe that we almost didn't want to believe that it might fall short in explaining like everything that's going on like within the universe. And so it almost feels like we kind of threw dark energy in there to like fill a pothole, like, in a sense.
Yeah, yeah. Because I think of like, I don't know, just like things that have happened in human history, maybe in health, where people say, oh, this was a miracle. And it's like, but was it? And then like later one day it maybe is explained, or alternatively, sometimes in health people explain a disease as a demon, and then later they go, oh, that was really just like a virus or something, or this was the result of some neurological condition or whatever, right?
Yeah, like there might
Anyways.
be a simpler explanation to it than just saying that it has to be this mysterious dark energy force.
Okay. Does anyone have any other questions for Simon? Well, Simon,
Yeah,
thank
I
you
got
so much for that. Oh,
a quick one.
Okay.
So Simon, you were mentioning that you were incorporating spin into the equation, and I'm wondering, could you somehow prove that on a small scale and how that would affect it? So if you get like a super heavy, dense metal sphere and you spun it really quickly, would that have an effect? Like, could you somehow model an equation around that? Is it looking at centrifugal and centripetal force? Like, are you kind of trying to use those concepts to integrate into general relativity?
Yeah, those are kind of the concepts that we are trying to incorporate. Um, Kind of hard to measure them, like in real life, but that's kind of the general idea of what we're trying to do. And that probably goes like along with like when you think of electromagnetic forces too, like repulsive forces, when two magnets are coming together and how we can measure that. So maybe eventually we'll get to the um like I'd say that you're definitely probably right that scientists out there probably did look at that spin factor and actually found a way to measure it like in terms of gravity, but that's not really like the part of our research that we did. We more just looked at the equation that represented that, or that best represented that spin, that torsion factor, and we included it into the calculations like in a way that had never been done before.
Okay, thank you.
No problem. And I have to be upfront and honest, like we more did the mathematical side of it. Like even in doing the research for the physics part of it for this presentation, like I learned a lot of new stuff too. So I'm definitely not an expert on it, but I do find it a really interesting topic, and I find it cool how we can represent it mathematically.
Well, you're well researched and you did a good job preparing for this, Simon, and you did an excellent job presenting. So thank you very much.
Okay, guys. Yeah. Thank you.
Emily, would you like to go next?
Sure. I'm just gonna